So I found a couple of past exam questions on waves. Here is one, the first one, that starts generally about waves and their characteristics, and then it continues with a Doppler effect. So let's start from this one. The first question says, state what is meant by the frequency of a progressive wave. Well, frequency, we can say, is the number of oscillations per unit of time, isn't it? How many oscillations are completed per second, in other words, that is the frequency, the number of oscillations, number of complete oscillations, perhaps complete oscillations per unit time. Per unit time. Okay. What oscillates now? But since we're talking about wave, we can talk about a point, because points in a wave, points in the medium where the wave propagates, oscillate. So the number of complete oscillations of a point of the medium or of the source or whatever, all of these would be correct. Now let us go to this question, which is the proper question after the definition. Now, it says a cathode ray oscilloscope is used to determine the frequency of the sound emitted by a loudspeaker. The trace produced, which is this one, the trace produced on the screen of the oscilloscope is shown in the figure. And we can see that one of these little squares represent 1 by 1 centimeters, and this is important because would give us the time base setting of the oscilloscope, which is 250 microseconds per centimeter. So each of these, one of these centimeters here represents 250 microseconds. In other words, they give us the period of the oscillations by counting how many squares we have. So 250 microseconds per centimeter. Show that the frequency of the sound wave is 1,600 hertz. Okay. So, well, here we can find, first of all, the period. And from the period, we can find the frequency of the wave. So, look at this. The period is the time taken for one complete oscillation, isn't it? So now let's see, if we go from crest to crest here, from crest up to there, that represents one period. And from here to there, if I go all the way to the end, it's easier actually. All of this would be one and another one oscillation, two oscillations. I say that because it's easier to see the squares from this point up to the end. So, and how many squares are these now? 2, 4, 5. It's all of them. It's 5 centimeters. From there up to there is 5 centimeters. I hope you can see it clearly on your screen, because 1 centimeter is 5 little squares. So from there up to there is 5 centimeters, which means now the period here, the period is half of it. From there up to there, it's half of it. It's 2,5 centimeters. And each centimeter corresponds to 250 microseconds per centimeter. So microseconds, now to change this into seconds, what can we do? This will be 2,5 times 250 times 10 to the power of minus 6 seconds, because the micro is 10 to the power of minus 6, isn't it? All right, so this now, if we do the calculations here, should give us 1,600, sorry, this would be seconds, no, it shouldn't give it, looking for frequency, sorry. All right, so this is the period. The frequency is the inverse of the period, isn't it? The frequency is 1 over period. So this would be 1 over 2,5. 2,5 times 250, according to my calculations, is 625 times the 10 to the power of minus 6. So we can put it on top. This is seconds here. So this now should give us the 1,600 hertz, 1,600 seconds to the power of minus 1, which is hertz. So this should give us the answer. All right. So this. So first of all, we find the period from the picture that we have on the oscilloscope. The period is given, of course, by the distance between two crests or two troughs, or 2 points in phase, and which corresponds to 2,5 squares, centimeters, this type of squares, I mean. And each centimeter here corresponds to 250 microseconds per centimeter. So we find the period, and from the period, then the inverse of the period is the frequency, and we find it. Okay. Now, the next question now concerns the Doppler effect. But by the way, I don't know if you, I found a video. We can hear the Doppler effect as it applies to sounds. Where is that now? Here. Find it. There. Let's listen to that. Let's make the sound higher. Okay. All right. Did you hear that? Did you hear that when the car approaches us and hoots continuously, we hear a higher pitch, wing, and then when it crosses us and passes away and starts moving away from us, we hear a lower pitch. It goes down again, the sound, lower pitch. I hope you heard that well on the video. And here we have a question that concerns the Doppler effect that we saw just now. It says the loudspeaker, okay, the loudspeaker that we were talking about before, and of which we found that its frequency was 1,600 hertz. We need this number now. Okay, so now this loudspeaker emits the sound in all directions, obviously. A person attaches the loudspeaker to a string and then swings the loudspeaker at a constant speed in a horizontal circle above his head. Okay, so the result of this is we're going to hear a Doppler effect phenomenon, because as the string rotates with a loudspeaker at its ends, sometimes the string comes closer to us as it turns, sometimes it moves away from us. So we're going to hear a high pitch, low pitch, high pitch, low pitch sound as the loudspeaker rotates in a horizontal circle and comes closer and further away from us. So now an observer standing a large distance away from the loudspeaker hears sound of maximum frequency of 1,640 hertz. So the maximum frequency that this person hears is 1,640. So they give us, in other words, the frequency of the high-pitched sound that we hear when the speaker is on its way closer to us. So this is the maximum frequency that we hear. The speed of sound in air is 330 meters per second. Okay, so this is not the actual frequency of the loudspeaker, because the actual frequency was 1,600 hertz. We found it just now. Now, the maximum frequency that this observer hears when the loudspeaker comes closer, approaches, is 1,640 hertz. Obviously, it's a bigger frequency. That is why we hear louder, a higher pitch. Okay, so this is, let's say, the f prime, the observed frequency. Okay, determine the speed of the loudspeaker, which is the source. In other words, we need to determine the speed of the source. All right. I hope you understand this problem. Eh? If you don't, just send me a message quickly so that we can discuss it again. All right. So an observer standing a large distance away from the loudspeaker hears sound of maximum frequency of 1640 Hertz. The speed of sound in airstream is 30. Determine the speed of the loudspeaker. Now, for us, when we need to apply the formula, the famous formula for that we use when in the Doppler effect, which is like the frequency that the observer listens, receives, the apparent frequency, is the speed of sound divided by the speed of sound. And here it's either plus or minus with the speed of the source. In your case, according to your syllabus, the Cambridge syllabus, you only deal with problems where the source might be moving relative to the observer. You don't deal with problems where the observer might be moving as well. So we have one less variable. So we see that in this formula we have f prime is the frequency that the observer listens. This is the frequency, the actual frequency of the source, which is the 1600 Hertz in our case. V is the speed of sound, which is this one, the speed of sound, which does not change, obviously, with no matter whether the source of sound moves or not. And Vs is the speed of the source that makes the sound. In our case, the source is the loudspeaker. So this is the speed of the loudspeaker. And this is what we need to determine here. Although there are a reasonable way to figure out what to use here, the plus or the minus. A rule that does not fail is that when the source of the sound, when the source and the observer, when the source and the observer approach one another, in this case, the source will be approaching because we consider only the source moving. The observer is always taken as stationary in your case. When the two approach one another, we take the denominator sign is minus. We take the minus sign in the denominator. Where I have written it there, it's not very clear. So we use the minus sign here in the denominator. If the source and the observer move further away, in other words, if the source moves away, let's say away, then we use the plus sign in the denominator. So in our case now, we an observer standing a large distance away from the loudspeaker hears sound of maximum frequency. It's when the maximum frequency is when the pitch is very high, where the source approaches the observer. So in this case, we have this approaching situation where we hear the maximum frequency, the higher frequency. So we're going to use the minus sign. So, all right, so let us rewrite this using the appropriate sign here in the denominator. So V divided by V minus V of the source times the actual frequency. And we need to solve for the speed of the source. We know everything else. We know the speed of sound. We know those two frequencies. Okay, we can replace the values or we can solve for the source. All right, because in your exam that you replace the values first, okay. the frequency that the observer listens is 1,640 hertz. I'm not going to write now units. And this is equal now to the speed of sound here, which is 330 meters per second, divide by the speed of sound 330 minus the unknown speed of the observer times this frequency, the actual frequency, which is 1,600 hertz. Okay, so here if we do the calculations, let's continue here. That will be 330 times 1,640 minus 1,640 times the PS, speed of the source, and this is 330 times 1,600. And what do we have here? This gives us 541,200. This one is equal to, what is doing? 528,000. Okay, so from here, if we solve for Vx, what is this now? Goodness, the source, the speed of the source. Okay, that's enough with calculations. This is how that will give us about 8. Well, fine here, 8,05 meters per second, which is we can say, to round it up to 2 decimals. I mean to 2 significant figures. 8,1 meters per second. I would think that this would be the correct answer here. All right. Now, there's one more question. Describe and explain qualitatively the variation of the frequency of the sound heard by the observer. Well, in this particular case, as we said before, it's because the loudspeaker, as it moves in a circle, sometimes it approaches the observer, sometimes it moves further away from the observer as it moves in the circle. So when it moves closer, when moving closer, what happens with the wavefronts that are emitted by the sound source? They come closer together. The wavelength decreases, the frequency increases, therefore. When moving closer, that means the wavefronts approach one another and the wavelength becomes smaller, which means the frequency becomes bigger. That is why higher. That is why becomes bigger. That is why we hear a higher pitch. Higher pitched sound. The opposite happens when the loudspeaker now starts moving away from us as it goes to the other side of the circle. Then when the loudspeaker moves further away, the wavefronts are emitted further and further away. So when it moves away, the wavelength becomes larger, or which is the same like saying that the frequency becomes smaller, lower frequency, lower pitch, low pitch. So we are going to hear a lower pitched sound. Continuously. These two happen repeatedly. This rise and fall in the frequency and the pitch that we hear. So there is this repeated rise and fall of the pitch that we hear, or the frequency. In frequency, we can say in frequency and pitch, because what we perceive as high and low frequency is the pitch that as a characteristic of sound. Okay, and that's enough. Okay, this is what they need to say. They want you to say, they want to see that you understand that when the object, the source of sound, moves away, you hear a lower pitch because the frequency is lower. When the object that emits the sound comes closer to you, you hear a higher pitch because the frequency is higher, because the wavefronts that you receive are packed up closer together, and the wavelength is smaller. It's better to have this visual image of what is happening. Let me see. I found some image. Now, where is this now? Who knows? Not this one. Yeah, like something like that. I hope you can see this picture of an ambulance approaching this observer. As it emits sounds approaching the observer, you see here the wavefronts pack up closer together. And the distance between two of these wavefronts actually is the one wavelength. You see the wavelength decreases. And the wavelength decreases means the frequency increases. And the pitch that we hear increases, it's higher. That is why we hear high-pitched sound. On the other side now, though, for the other observer on the other end, where this observer now sees the ambulance moving away, which means now the wavefronts that this observer receives are further spaced, further apart, spaced. And you see two wavefronts. The distance between two wavefronts again corresponds to one wavelength, and we see now these wavelengths are bigger, which correspond to a smaller frequency and a lower pitch. That is why this observer here lowers the pitch as the ambulance moves away. So it's good to have, in other words, this image in our mind when we talk about pitch and the frequencies and wavelengths, when we talk about the Doppler effect. Perhaps it helps to start thinking in terms of wavelengths, because one wavelength is the distance between those two wavefronts, which are closer together. We can see with our eyes that these wavefronts are packed closer together, which means the wavelength is small here. And the frequency follows the opposite rule. If the wavelength is small, the frequency is large. So big frequency here, high frequency, high pitch. On the other hand, we have large wavelengths, small frequency, low pitch. And I hope this makes sense. All right. And where are we now? Where is our problem? I have no idea where it is. It was this one. Yeah. Okay. Now, this is enough now, but there are quite a few problems though with a double slit experiment, which is we are getting now in a different territory. Maybe we can start this problem now. It's only this page, actually. It's not a lot. We have 10 minutes. Yeah. And next week we can continue. So this is another problem now. The problem 5. It's on the same paper, but it's a different problem now that deals with. Here we have a double slit experiment, or actually a diffraction grating, but it's the same. Similar, very similar. Okay, let us start discussing this and we'll see how it goes. State what is meant by the diffraction of a wave, okay. In general, diffraction of a wave means the bending of a wave, but I suppose here they mean about a light wave, in which case they talk about the formation of a diffraction pattern, but anyway, that's it. It is just a definition. Now let's go to B, because we don't have enough time. Laser light of wavelength 500 nanometers, so they give us a wavelength, is incident normally on a diffraction grating. The resulting diffraction pattern has diffraction maxima up to and including the fourth order maximum. Okay, so we have a diffraction grating here, and the light goes through, and here we have, say, the screen, and we see up to 4 and including 4 maxima. Okay, so the first maximum will be here in the middle, then we have a second one and a third one, and then we have a fourth one. Maximum. Okay, so here we have maximum. We cannot see any other maxima. 1, 2, 3, and another one 4. Okay. And including the fourth order maximum. Calculate for the diffraction grating the minimum possible line spacing. When they say line spacing, they mean the difference between two slits in the grating. Okay, which a grating can have 300 slits, or it could have 600, can have more, or even more than that. But they ask for the distance between two slits in this grating. So generally, when we use the grating, the diffraction grating, we use this formula: d sine theta is equal to n times lambda, where lambda is the wavelength of light. D is the distance between two slits in the grating. N is the order of maxima. The first one is here with n equals 0. And the next maximum is at n equals 1. The next n equals 2, and so on. All right. So the line spacing, what they mean here by line spacing, they mean they want us to find this d. All right. And they say that the resulting diffraction pattern has diffraction maxima up to and including the fourth order maximum, the fourth order, which means they give us that that n is up to 4. This n here is supposed to be 4, and that is the last maximum that we are going to see from this grating, which means if we cannot see anymore, is that this angle now becomes like too wide of the next maximum of order 5, for example. We cannot see the order 5 because it's like it has disappeared, because we're talking about an angle, very wide angle, up to, we consider this angle would be 90 degrees. So the maximum thing that we can see represents, they give us some information about this angle theta. If we assume that this angle theta becomes 90 degrees, we'll have the sine of 90 degrees. We have to replace this angle with 90 degrees because we cannot see anything else anymore. And this will correspond to the maximum of n4 equals to 4. And the wavelength is okay, it's given. All right. So from here now, the sine of 90 degrees actually is 1. Okay. So we can simplify this as d equals to 4 times lambda, which is 500 nanometers. So let's replace the value here. The 500 nanometers. Well, nanometers now, nano is 10 to the power of minus 9 meters. And this, okay, 4 times 500 is 2000, which will be 2 times 10 to the power of minus 9 minus 3, that will be minus 6 meters. So this will be the width, I mean the line spacing of this diffraction grating. So our line spacing here, which is the distance between two slits on the grating, is 2 times 10 to the power of minus 6 meters, because they show meters. Otherwise, we could say, we could write our answers to micrometers. But because they have meters here, we'll leave the 10 to the power of minus 6. Okay, so this is our answer here. The line spacing, all right. So that was a kind of tricky question, because we had to understand what they mean by the resulting diffraction pattern has diffraction maxima up to and including the fourth order maximum, meaning we have to understand what they mean. That they mean that we cannot see any further maxima above, beyond the fourth order, which means that then that the beam spreads so high, so wide, that really makes a 90-degree angle. And we need to replace this in our formula, which is the general formula, with 90 degrees here. So that was quite tricky to figure out. But once we figure that out, the rest is actually easy, because the sine of 90 degrees is now 1, and we solve the problem and we find the D. Okay. This light now, the light in B, the light which was 500 nanometers, is now replaced with red light. State and explain whether this is likely to result. Oh, it's 12 o'clock. Okay, we can discuss this. We can continue next week because this is quite an important question. And if they give you gratings or double slits experiments, perhaps they will ask you to compare what happens when you change the color of light, because the pattern that you see sometimes becomes broader or sometimes becomes shrinks, becomes narrower, depending on the wavelength of the light. So we'll discuss it next week. Okay then, sweetie. Yeah, so we'll see you next week.